Hello and welcome to today's webinar. My name's Chris Ball, and I'll be your host and moderator. Today's webinar is Corrosion 101, Causes and Assessment Strategies, sponsored by the Concrete Preservation Alliance. If you have an interest in corrosion and service life extension, then I think you'll really find today's webinar of interest. And we'll be covering the basics of corrosion, as well as corrosion of steel in soil and water, exposed steel, and the causes, effect, and detection of corrosion. As I mentioned, this webinar series is sponsored by the Concrete Preservation Alliance, in particular, some of the members, Vector Corrosion Technologies, VCS Engineering, Vector Construction, Fosrock, and Structural Technologies. The home of the Concrete Preservation Alliance is wesavestructures.info. And this is the website where you registered for today's webinar. I also invite you to come back to the website and be able to look at some of the other resources that are available where we promote best practices in service life extension and sustainability of concrete structures. And in particular, I just wanted to draw your attention to the free environmental impact calculator, where you can put in a quantity of concrete that will be rehabbed or rehabilitated. You can determine the social impact of those activities. For example, if you use, just say you have a structure with 10,000 cubic meters of concrete, if you put that into the calculator, that would show you that you're effectively preserving or avoiding the emissions of 6,000 metric tons of carbon dioxide and the consumption of 1.2 million liters of potable water, as well as other consumption of natural resources and production of solid waste. So I'd like for you to come back and take a look at the calculator, and I think you'll find it very useful. You'll see on your screen an opportunity to offer up some questions, and so we will have some question and answer session. And as usual, we encourage questions. We love questions. You can ask as many as you'd like. We will be giving away an Amazon gift card, $100 Amazon gift card, but we can't award that unless you use your name in the live chat. So we make sure that it's not an anonymous question. And then after today's webinar, the presenter will pick the best question and we'll send you the gift card. And speaking of the presenter, I'm really excited to have back Pratik Murkut, who specializes in metallurgy and materials engineering and is a senior project manager for VCS Engineering. Pratik is a professional engineer, certified cathodic protection specialist, and a proud graduate of Oregon State, where he received his PhD. And you'll see all the other information on the screen regarding Pratik's credentials. But Pratik will be providing his information with a lot of insight. So I encourage you guys to, once again, ask as many questions as you'd like, but I'd like to turn it over to Pratik.
Thank you so much, Chris. Can you hear me okay?
Yes.
Wonderful. Hello, everyone. Thank you for taking the time to join today's presentation on Corrosion 101. It's going to be kind of a refresher for high school chemistry. I'll be going into how the energetics of the corrosion cycle work, what are the different exposure conditions where a metal is exposed, This presentation will mostly be limited and focused to steel and structural steels. I won't be discussing other metals or alloys that are typically used. I'll also discuss the investigation tools for various environments like concrete, water, soil, and then go into the conclusions. So when we are talking about steel or the structural steel, we find it in the earth in the form of a mineral ore or iron ore. That's the starting point. And in terms of the energetics, the mineral ore or the steel ore or the iron ore has a really low energy when we find it in the native state. That is the starting point. But these mineral ores or iron ore, they are practically unusable because of no strength or extremely brittle nature. And that's why we need to refine them to make it into a usable product. And that's where we put in a lot of energy into it during the refining process. During refining, we put a lot of energy, and as a result, we get steel, cast iron, ductile iron, or wrought irons. These are all the engineering alloys we use. And when we use these alloys to make some engineering products like rebar, sheet pile walls, PT strands, post-tensioning strands, all kinds of different steel applications. But these products have a really high energy state because of the energy we had put in during the refining process. And when these steel elements are exposed to nature, the nature would do its best, what it does best. It's going to take the energy back from it. And that's where the corrosion comes into play. Corrosion is just one of the ways where nature will take the energy back from the system, and the system will try to lower its energy. And as a consequence of corrosion, we find rusting happening on the steel and effectively section loss and failures. And when the corrosion product or the rust forms on the steel, effectively you're going back to the same state we started with, essentially iron oxides and hydroxides, and effectively that's the iron ore we started with. So you are completing the circle in a sense, in terms of energy and also in terms of the phases that are formed. For any corrosion reaction to happen, you need four components. You need ACME, ACME. A is anode, C cathode, M metal, and E electrolyte. Corrosion is an electrochemical reaction, meaning it involves transfer of electrons and also it involves transfer of ions. Transfer of electrons happens through the metallic path, which is the steel itself. Transfer of ions happen through the electrolyte, which can be concrete, soil, air, or water. And then there comes the anode. Anode is where the section loss happens. Anode is where the corrosion products form, and anode is where you would see loss of section and resulting in the reduced load bearing capacity or loss of function. On the contrary, cathode is the protected section of the system. So as an example, here you see a bunch of rebar in concrete, and you see rust formation on the rebar, and that's where the anode is. Whereas on the other side, you see some protected sections of the rebar, that's where the cathodic section is. The rebar itself acts as a metal, and concrete itself is the electrolyte. It can be soil, water, or air. So to take the takeaway point of this slide is you need four components, ACME, ACME. If you try to remove any one of the four components, the corrosion reaction would cease to exist, but it's easier said than done. But we have other ways to mitigate corrosion or reduce corrosion. For this presentation, I have sectioned steel into two kinds in terms of exposure. One is the embedded steel. When I talk about embedded steel, I'm just talking about steel that is embedded in concrete, grout, or mortar. And the second category I have decided to use is exposed steel. It can be atmospheric exposure, marine exposure, or soil exposure. Let's talk about concrete first. As we all know, concrete is highly alkaline environment, pH greater than 13. But at the same time, concrete is porous in nature. So it's going to absorb and adsorb anything that comes in contact with. If your concrete element is exposed to de-icing salts, chlorides and moisture will get in. If your concrete is exposed to marine exposure, again, the chlorides and moisture will get in. If your concrete is exposed to carbon dioxide or carbon monoxide, which is essentially a lot acidic, carbon dioxide and carbon monoxide will get in and acidify the concrete. So because of its porous nature, it will absorb a lot of the species that result in corrosion of steel. Concrete performs exceptionally well in compression, but does not do well in tension. And that's why we need steel reinforcing to make structural elements or concrete elements. So when a rebar is exposed to good quality concrete of pH greater than 13 or a highly alkaline environment, a passive oxide layer forms on the steel. That is where a really strong oxide layer or a hydroxide layer forms on the steel, which is adherent to the steel surface. And this is what protects the steel from further corrosion. Now, there is a document for design guide for bridges for service life. It's a Sharp 2 document, and it lays out typical causes or typical species that cause corrosion of steel in concrete. And the two main culprits are chlorides and carbonation. And we'll get to this when we talk about subsequent slides. But as I said, concrete is porous in nature. It's going to absorb anything that comes in contact with it. Let's say if chlorides get in because of de-icing salt or marine exposure, or carbon monoxide or dioxide gets in because of vehicle emissions or industrial exposure sites, then it will try to destroy that passive fill. These two species will depassivate the steel or destroy that passive oxide film that was initially formed in the good quality concrete. And as a result, you start having rust on the rebar. This is where corrosion happens because of these two species. Now, the obvious question to ask is, why is corrosion a big issue? The answer is, it's the volume of the rust that forms on the steel. When you're talking about corrosion of steel, when you're forming rust, you can see there are many phases or many rust phases that form on the steel. And their relative volume to the steel would be on an average 3 to 4 times the volume of iron. It can get as high as 6 or 7 times the volume of iron. Now, to accommodate that space or to accommodate that volume, you need space in the concrete. And that is where you tend to push out the concrete away from the rebar to create some space for the rust. So when corrosion products form on the steel, they tend to push out the concrete away so that they can have some space in the matrix. Typically, this is what it looks like. You start with a good quality steel, good quality concrete, everything is good. The chlorides get in, or the carbon dioxide gets in. They tend to corrode the structure, corrode the steel, and that's where the rust product forms. It pushes the concrete away. That's where the cracking happens. That's where it provides a direct pathway for more chlorides or more carbon dioxide or moisture to get in. Once the cracks form, the rates can go up, and that's effectively what leads to delaminations and effective spalling. And that's where you focus on the repair side of things. I think this is a good place to see if we have any questions. Chris, do we have any questions on the energetics or basics of corrosion?
Yes, actually, we have a question from Jack. I think it's a good question. What is the difference between precast and post-tension structures? And I assume the question is more specific to corrosion of different steel alloys. Okay. And then you start thinking about post-tension structures, you have bonded and unbonded post-tensioning as well. So maybe just some thoughts on that.
Right. Oh, that's a really good question. So when it's about comparing your post-tension structures or pre-tension structures with a conventional steel reinforced structure, the key difference would be the tolerance for section loss. When it comes to conventionally reinforced structure, I would say you have more tolerance for section loss because the stress levels or the strain levels on the steel elements is not so high. But when it comes to post-tensioning, bonded, unbonded, or monostrand, your tolerance for the section loss is a lot less, especially because even a slightest section loss under that levels of stress can have catastrophic failures. So that's one. And second is in terms of the warning or the warning signs, I think you tend to see more warning signs for conventionally reinforced structures because the crack would form and then effectively the concrete would spall. But when it comes to post-tensioning structures, maybe the rust product that is forming on your strands, they are completely encased in the metal duct for the bonded post tensions, or for the unbonded post tensions, the rust product can be completely encased by the plastic sheathing that's around around the steel. So you might not have enough warning signs in terms of the failure of the structure. So that is how I tend to think about distinguishing between a conventionally reinforced structure and a post-tension or a pre-tension structure.
Yeah, because we run into all those conditions. So excellent.
Perfect. Thank you. All right, let's move on to condition assessments. Now we know how the energetics work, why corrosion happens. It's all about energy and how corrosion happens. Let's go into what are the typical investigation tools for steel embedded in concrete. And for this presentation, I have divided those typical test methods into three categories. One is non-destructive evaluation, where you do not make any indents or any damages to the concrete. Second is semi-destructive evaluation. It can be corrosion potential mapping or corrosion rate measurements, where you need to make a connection to the steel. And the third is destructive evaluation or concrete sampling, where you actually have to take the sample from the concrete element to do some chemical analysis or to do some measurements of the section loss on the steel. Let's get into the non-destructive evaluations first. So visual inspections is one of the most primitive techniques we use for assessing the structures, but it is often too late in the process of deterioration. By the time you see a crack or you see a spall, the corrosion has already happened. Typically, you tend to see signs for efflorescence, spalling, section losses. You can see rust staining or water staining. And by the time you realize these issues, it's often too late in the process. We also heavily rely on delamination surveys or hammer sounding surveys or chain drags. Essentially, when you perform a hammer sounding or a chain drag survey on a concrete element, you tend to hatch out those elements. You mark out those areas on the concrete deck, let's say, and then when it goes out to bid for the repairs, you see a sudden uptick in the repair areas or the repair quantities, and that's primarily because of a couple of things. One is hammer sounding or chain drag is not able to pick up issues of micro cracking. You might not be you might not be able to hear the micro cracking or the areas with micro cracking. It might not sound hollow, but it has a weakened area or less compressive strengths. Does that mean the damage is limited to that micro cracked area beyond the hashed area? Well, not really, because the damage can further go beyond the micro cracked area, which is shown in red. That is the area where active corrosion is happening. The steel is actively corroding, but it has not reached the point that it would cause a cracking or delamination or effectively spalling. So that's why you tend to see a sudden uptick in the repair quantities when you just rely on hammer sounding and visual inspections. My recommendation would be we need to use some advanced techniques to accurately assess, okay, this is where my damaged concrete is, and this is where I need to focus my attention for future corrosion mitigation or repairs. The more advanced techniques we often use in conjunction with hammer sounding and visual inspection is cover depth surveys using ground penetrating radar, or GPR as we call it. GPR technique essentially probes the subsurface condition of the concrete by transmitting a high frequency electromagnetic wave into the structure and detects the energy reflected from the interface between the material of different electrical properties such as dielectric constant or conductivity. So in case of concrete, or in context of concrete, these structures can be, these interfaces can be reinforcement concrete interface, air concrete interface, or asphalt concrete interfaces. The greater the contrast between the electrical properties, the more energy that is reflected back to the antenna, and that's what we use to assess the cover depth. So as an example, when a GPR unit passes over the metallic object like reinforcement, like a rebar or a post-tensioning strand, the electromagnetic waves are reflected back to the receiver in the GPR antenna and is graphically manifested as a hyperbola. And this is what a typical GPR scan data looks like for a reinforced concrete, with each hyperbola representing a presence of a rebar. Using this technique, we can gauge we can have various information from the structure. GPR units come in all shapes and sizes, and depending on the feature of interest, the frequency of the wave that is put into the concrete should be selected. And since the signal penetration and the spatial resolution is also dependent on the wave frequency, it's really important to pick a appropriate GPR unit. So for instance, a high frequency GPR unit are used to look at the shallower features like concrete cover or reinforcement spacing, whereas low frequency GPRs are typically used for investigation of fill layers and locating utilities. So typically high frequency antennas have a shallower depth of penetration, but they have really high resolution, really high spatial resolution. Low frequency antennas have greater depth of penetration, meaning they can look a lot deeper into the concrete or soils, but they lose out on the resolution. And here is a table showing the antenna frequency and appropriate range or approximate range of depth for penetration and typical applications we see. So shallowers are usually high frequency GPRs, whereas for deeper penetration or deeper look into the structure, you tend to have a low frequency GPRs. One of the most key pieces of information is concrete cover, because this defines how much risk it poses to in terms of the corrosion of steel. The lower the concrete cover, the higher is the risk for the rebar corrosion, because it's going to take a lot less time for chlorides or carbon dioxide to get into the concrete if you have a shallower concrete cover. If you have a deeper concrete cover, obviously the time to reach the rebar level increases significantly. You can also plot concrete cover information in a 2D heat maps. This is kind of a heat map of the columns, and it will tell you spatially as to where the areas of low concrete cover are, and you can focus your attention for corrosion mitigation or repairs in particularly those areas, because those areas would be highly prone to corrosion. In addition to concrete cover, it can tell you what is the rebar spacing or how many mats of rebar are present. And if for an experienced eye, it can also tell you, okay, if there are post-tensioning strands present or what is the distribution of those rebars. And it can help you assess a really good layout for corrosion rate measurements or other techniques. There have been claims in the market that GPR can tell you what exactly is the issue with the concrete. But the thing is, GPR can only tell you the locations where you can have a potential defect. In the image shown here on the bottom, you see the left side of a typical GPR scan shows a diffused signal. You cannot really see a clear hyperbolas or clear rebar. Whereas on the right side, you can see a specific, very clear peak, which is a sign of sound concrete. Whereas on the attenuated side, on the left side, that is an area of potential defects. GPR cannot tell you what exactly is the defect. It cannot discern between moisture content or chlorides or honeycombing or voids. It can only tell you, okay, this is where the location of potential defect is, and we need to investigate it further using various different techniques. You cannot solely rely on GPR to tell you locations of delaminations or any other potential defects. Another technique we often use in field is concrete resistivity. Concrete resistivity is one of the key factors that define the corrosion kinetics in reinforced concrete. When I say corrosion kinetics, I'm talking about the rate of corrosion. Essentially, in field, you use something called as a Wiener probe, where it has 4 probes. The outer 2 probes pass a current between them, like the outer 2 probes, and the inner 2 probes measure the resulting potential change. And this is how you calculate the resistivity of the concrete. Concrete resistivity directly affects the corrosion rate of the embedded steel by controlling the ionic conductivity through the pore solution, which is critical for corrosion process. And this test can be performed on concrete element or can also be performed on concrete cores. But one thing to note here is the concrete resistivity measurements are highly influenced by presence of metal. So when you are performing this test on a concrete element, precaution should be exercised to avoid rebar at all cost. Because if you're performing the concrete resistivity measurements on a rebar right on top of the rebar, it will give you false values, and it's a high chance of misinterpretation of the resistivity value, because presence of metal object can lower the resistivity value significantly. So Typically, we prefer to do concrete resistivity measurements on concrete cores instead of taking measurements on the element. We extract the concrete core, maybe for, let's say, chlorides or compressive strengths or petrography. When you extract the core, you might as well just perform concrete resistivity test on the core, and that way you eliminate the metal issue. Um, Typically, high resistivity values can be related to low corrosion rates, whereas if your concrete is highly conductive, then it can accelerate the corrosion of steel. Uh, a lot of factors affect the concrete resistivity. It depends on your moisture content, your ionic conductivity, the temperature. If you take a measurement on a warm sunny day, and if you take a measurement maybe a week later when it's overcast, then you might get different measurements just because of the temperature variation. So typically you tend to take multiple locations, multiple measurements over multiple period of time, and that will give you an average of the concrete resistivity values. But if you do it on a concrete core, then you can have a surface saturated dry state of the concrete core, and you can get consistent measurements constantly. As I mentioned before, if the resistivity is really high, the risk of corrosion is negligible. But if you have a highly conductive concrete or less resistive concrete, then the risk of corrosion increases significantly. In addition to concrete resistivity and GPR, we also use some acoustic techniques to probe the structure. Typically, we use impact echo and pulse velocity. Essentially, we send a sound wave into the concrete and we wait for the reflections to come back, and we measure the time and the velocity of the sound that is passing through the concrete. Typically, that sound can be induced into the concrete using a ball peen hammer, or it can be a transducer initiated sound pulse. In terms of the instrumentation, both the technique, that is impact echo and pulse velocity, have the same setup where we use um, steel ball bearings or BBs and a pneumatic BB impactor as an energy source, where we put the stress wave into the concrete using an impactor. And then we have a piezoelectric ceramic sensor array that is placed right next to the impactor. So you make an impact and you measure the signal using those sensor arrays placed right next to the impactor. So in terms of analysis, when you take the shot, you just analyze the data. And in terms of the sensor placement, the first two sensor, they analyze the reflections as to how long it took the sound for it to reflect back. And sensor 1, 3, and 4, they focus on what was the velocity of the sound using the frequency domain. This is typically how the sound or the acoustic wave would travel through the concrete. It reflects on any cracks or any defect that is present in the concrete, and it will also reflect back from the back surface of the concrete. That's essentially what the sensor is measuring. As the name suggests, impact echo is waiting for the reflections to come back, measuring the reflections, looking for the reflections, and it can give you an idea about the thickness of the concrete elements, if there are any potential delaminations, and it can also give you an idea about the strength of the concrete in the thickness direction. Whereas for the pulse velocity, we are looking for the velocity of sound traveling through the concrete. It can give us modular values, give an idea about micro cracking, and also any potential defects. And it can give us the strength of the concrete, I mean the in situ strength of the concrete. And there is a really good correlation between the in situ strength and the cylinder break tests. So when it comes to impact echo, you don't necessarily have to take concrete cores from the structure. Impact echo or pulse velocity can give you compressive strength values or the dynamic compressive strength values. But if you were still to extract some cores, then this is a really good starting point. This is what you would use to guide your decision for extracting the cores. You can lay out the data, impact echo data, on a 2D heat map. It will tell you exactly where the weak zones are or where the compressive strength of the concrete is low. It will also tell you the areas of high compressive strength. So you can decide where to take the samples. and then it can analyze section thicknesses up to 4 feet. But if you want to analyze thicknesses greater than 4 feet, then we go into geophysical range where we need to alter the sensor spacing, and we can still get it done. Now, in addition to non-destructive testing, we also perform some semi-destructive testing where we need to make a connection to the steel in the concrete. One of the tests is corrosion potential survey. You make a drill connection, you make a drill hole, you locate the rebar, you make a drill hole, you make a connection to the steel on one side. On the other side, you use something called as a reference electrode. You place that electrode on the concrete surface and you connect it to a voltmeter and you just measure the values that are being read on the voltmeter. This test tells you the probability of active corrosion and how widespread the corrosion issue is in the concrete. It effectively measures the potential difference between the embedded steel and the reference electrode that is placed on top of the concrete. This is a gentleman who is doing the test. They have hashed out or they have marked the areas of potential delaminations, and we wet the concrete surface, we make the connection to the steel, and we take the measurements in a grid pattern, maybe a 2 feet by 2 feet grid, or maybe a 1 feet by 1 feet grid, based on how granular the data is required. This is a sample corrosion potential survey map of a concrete deck, and you see a lot of corrosion hotspots here. If you have slightly warmer colors or reddish colors, that's where the corrosion hotspots are. You see a lot of corrosion hotspot towards one end of the bridge or one edge of the bridge. However, you also see these two hashed out areas where you don't see any corrosion. They are in the passive area. More greener shades, that's what you see here in these two areas. And there is a good reason behind it. What we saw was when we were doing the corrosion potential survey of the deck, these two areas were the areas of concrete patch repair. Remember, at the beginning of the presentation, I mentioned that if your steel is exposed to good quality concrete, highly alkaline concrete, which is essentially the repair concrete, in this case, you tend to have a passive layer formation on the rebar. And that's what you see in the corrosion potential measurements. Whereas right outside these patch repair areas or the concrete repair areas, that's where you see active corrosion happening, because you would still have chloride contaminated concrete right outside the patch repair areas. Essentially, this effect, what we call it, is called ring anode effect or incipient anode formation, and we can talk about that later. This is another example of a corrosion potential survey of a crosswall from a bridge in Harrisburg, Pennsylvania. This crosswall, at least the left side of the crosswall and the bottom sections of this wall, were actively corroding. Rightly so, because the chloride contaminated runoffs from the decks were running off onto this wall, which was right under the expansion joint. And that's why we saw a lot of corrosion, because of chloride contaminated water just wetting this wall constantly. So corrosion potential survey can give you statistics about how active the corrosion is, how widespread the corrosion is, and where the areas of active corrosion are located. In addition to corrosion hotspot, we often run linear polarization test or corrosion rate testing, which is governed by ASTM G59. It's typically a 3-electrode setup. It measures the instantaneous corrosion rate. It won't give you an average corrosion rate. This technique is highly susceptible to external factors. Your corrosion rate measurements can quickly change based on relative humidity, moisture content, chlorides, carbonation depth. So I would take results of this test with a grain of salt. I would not use it to calculate the exact corrosion rates unless you do this test multiple times over multiple locations for multiple duration of times. And I would typically use this test for determination of the current requirement. If you know that your structure is experiencing corrosion, I would use corrosion rate measurements just to get an idea as to how much current is required so that I can provide effective service life at the end of 20 or 25 years. As I said, this technique is highly dependent on external factor, whether your instrument is calibrated or not, what is the oxygen availability, how much steel surface area is below the counter electrode or the anode you're trying to use to press the current, and if there are any chlorides, what is the concrete resistivity and moisture content. There are third-party manufacturers who make corrosion rate devices. Just that caution must be exercised while using corrosion rate devices. And it should be the data derived from the test should be applied properly because, as I said, this is an instantaneous corrosion rate measurement. It cannot give you an average value. It's the value of corrosion rate at that point in that moment in time. It can change after 5 minutes, 10 minutes. It's a highly variable test. In addition to non-destructive and semi-destructive testing, we often do concrete sampling to get more idea about the structure. At the beginning of the presentation, I mentioned that chloride is one of the key species that cause corrosion of steel. That chloride can come from marine exposure or de-icing salts, anti-icing salts, or chemical or industrial environments. And back in the day, in some cases, we have seen cast in chlorides. The unfortunate part of chlorides is they are never consumed. They only act as a catalyst. They're never consumed in the reaction. They will always be there once they get to the rebar depth, unless something specific is done to remove the chlorides away from the concrete or away from the rebar, from the concrete. So chlorides just act as a catalyst, and effectively, we need to know what is the chloride content at the rebar depth so that we can assess the risk of chloride-induced corrosion. And to do that, we often perform chloride threshold test or chloride contamination measurements. We do concrete sampling. We either take a concrete core or a powder up to the rebar depth, and in some cases beyond the rebar depth. And this is what a typical chloride profile looks like. If your concrete deck is exposed to high levels of de-icing salts, then obviously you would see a lot of chlorides at the surface. And as you go down the depth, the concrete might have lesser and lesser amounts of chloride. The key piece of information to be derived here is what is my chloride level concentration at the rebar depth. There are two relevant pieces of information that we need to plot to make more sense of this data. One is what is the average concrete cover depth or what is the average rebar depth and the error associated with that, and what is the corrosion initiation threshold or critical chloride threshold. Critical chloride threshold is the minimum amount of chloride that is needed for corrosion to initiate. For our modeling purposes or for our testing purposes, we use that concentration to be 350 ppm by mass of concrete, or we use 1.5 pounds per cubic yard of concrete. That's essentially what we use it as a baseline. So the way you read this data is, if your chloride content at the rebar depth is above the threshold, then your rebar or the steel reinforcing is at the risk of chloride-induced corrosion. If this last point were to be below this line, then the way I would read it is currently there is no risk for corrosion-induced chloride-induced corrosion, but as of now, but it might be a risk in future. So you need to be on lookout for the chloride measurements at the rebar depth. In addition to chlorides, I had mentioned that carbonation is one more factor that affects the corrosion. Effectively, when your concrete, for instance, let's assume a parking garage, the undersides of the slabs, they're constantly exposed to vehicle emissions, or let's say an industrial site where it's exposed to carbon monoxide or carbon dioxide. Carbon dioxide gets into the concrete, the porous concrete, and it reacts with the free lime or the calcium hydroxide that's in the concrete. That is what it gives the high pH to the concrete. When it reacts with the free lime, it results in the formation of calcium carbonate. And effectively, what we see is lowering of the pH. And there is a quick and easy way to see if your concrete is carbonated or not. If you extract a chloride sample, if you extract a concrete sample or a concrete core from the element, you can spray it with a pH indicator spray or a phenolphthalein spray, what we call it. It will tell you if the pH of the concrete is in the acidic area, acidic range, or the alkaline range. If the color of the concrete after spraying that spray turns to pink or purple, it means your concrete is high pH. If the concrete turns colorless, it means the concrete is acidic. So for instance, you start with the really high pH concrete, it's a good quality concrete, and then your structure grows old, the carbonation front starts approaching the rebar depth. And effectively, you see that at the rebar depth, the carbonation front has reached. This is where problems start to happen. Because you are in a low pH environment, the rebar will start rusting. It will start formation of rust. Obviously, you will have some moisture to support that corrosion process. But just because of the low pH environment, you can have the rust formation. Remember, for passivity, you need high pH. You need highly alkaline environments, but carbonation that reduces the pH. In addition to chlorides and carbonation tests, we often do section loss measurements. So essentially, if we suspect that there is severe section loss or there is severe carbonation of chlorides going on into the concrete, we often expose the concrete. We often open up the concrete and expose the steel that's within. We have done these tests on conventional reinforced concrete or on the pre-stressing concrete as well. Effectively, you try to measure the remaining diameter or remaining section of the steel reinforcing. You chip out the concrete, you open up the concrete, you expose the steel, and you take the measurement. You compare it with the original reinforcement that was used, and you calculate the section loss. Obviously, if you tend to see a higher section loss, then that's a concern. And obviously, that can call for more corrosion remediation or concrete repairs in the future. Now, this was all about chlorides and carbonation and rust resulting in cracking of the concrete. So the rusting of the concrete came first, and then the concrete cracked. But it can happen the other way around as well. If your concrete is exposed to freeze thaw effects, or if your concrete is susceptible or the aggregate is susceptible to alkali silica reaction or sulfate attack, then you can have concrete cracking first. Once the concrete cracks, it can provide a direct pathway for the chlorides or carbonation or water or oxygen to get in, and that's where you can have accelerated rates of corrosion. Now, this is the other way of looking at it. You just have concrete cracking first, and then the reaction, and then the corrosion happens. One way to find out if your um, concrete structure is suffering from a freeze thaw damage, or is it susceptible to alkali silica reaction or sulfate reaction, you use what is called as petrographic examination or petrographic analysis. It is effectively a microscopic examination. It gives you an idea about micro cracking, macro cracking. If your cement or concrete is completely hydrated, what was the water to cement ratio? It's a very in-depth examination of the concrete. It can also give you an idea about what kind of what kind of aggregates were used. If those aggregates are susceptible to alkali silica reaction or alkali carbonate reaction, and if you are seeing any freeze thaw damage. It can also tell you the nature of the voids you have. It can tell you the air void content, and it can tell you, okay, if your concrete is susceptible to freeze thaw damage or not. So petrographic examination is really powerful, and it will give you a lot of information. These are a couple of microscopic images we have done over the period, which shows typical defects we encountered: freeze thaw damage, carbonation, sulfate attack, alkali silica and carbonate reaction, and it can also probe microbial induced corrosion of concrete. Now, this was about embedded steels. This was about steel embedded in concrete. Let's talk about exposed steel. The steel can be exposed to water, it can be exposed to soils, and it can be exposed just to air. Well, air is an electrolyte, but it's a poor electrolyte in terms of the testing. When it comes to waterfront structures, you have a series of tests you can run to see if your water is corrosive or not. One way to do it is just check for the salinity and the conductivity of the water, and it will tell you if the water is highly saline, how much chlorides or sulfate it has. You need to run for ion concentration test. You need to also test for hardness and alkalinity, especially if your water is fresh water. It does not mean that if you have a fresh water that you won't have any corrosion. You still can have severe corrosion in fresh water. Typically, the rates are low, but you run a test called Langmuir saturation index, and that can tell you if your water is corrosive or not. And this test is typically run for freshwater sources. When it comes to sheet pile walls, or let's say edge piles or steel piles exposed to soils, You need to have resistivity measurements of the soil. You need to have what the pH of the soil is, if the soil is acidic or not, if the soil is contaminated with chlorides or sulfates. Because if a steel element is exposed to soil contaminated with chlorides, then obviously it's a major risk in terms of corrosion. But if your concrete structure is exposed to chloride contaminated soils, the concrete will leach the chlorides in. It will take the chlorides from the soil and it will cause corrosion of the steel. There is a big potential for that. And we have seen that happen over and over again because concrete is porous and it will absorb anything and everything that comes in contact with it. Chloride in the soils is one of them. And then when you have air exposed soils, there are only a few handful of tests we can run. So let's talk about the air exposed chloride or the other exposure environments for the steel. First is atmospheric exposure. When you have atmospherically exposed steel, it can be coated or bare. You tend to have very limited set of tests you can run. What we have seen over time is if your steel element, like a bare steel element, is exposed to marine environment, then you have a really high section losses rather quickly because of airborne chlorides. That moist air can sit on the steel surface, it can form microcells and it can corrode the steel or pit the steel. Whereas in rural environments where the air is relatively cleaner and you have very less contaminants, you would have a significant drop in the section losses over time. So we need to be mindful of what kind of steel it is, if it's coated or uncoated, and what kind of environment it is, because that will help us design the structures better. Maybe we can have more sacrificial thickness, or maybe we can have more effective coating for those steels. When it comes to marine exposed steel or soil exposed steel, especially marine exposed steel, your corrosion rates are highly variable. And for marine exposed steel, the corrosion rates or the section loss is primarily driven by the presence of oxygen, which is responsible for the cathodic side of the reaction. You see that you have severe section losses in the tidal zone or the splash zone, whereas in the mud area or the subsoil zones, you have significantly less section losses, and that's primarily because you don't have any oxygen whatsoever or very less oxygen below the mud line. And you have constant wetting and drying cycle in the splash zone, which causes an accelerated form of corrosion. So when it comes to air exposed steel, you have, as I said, very limited options in terms of testing. One of them is ultrasonic thickness measurements. Essentially, that's a tiny probe. You place it on the concrete, you place it on the steel surface. You have a flat, clean surface, and you test for the section loss of the remaining section of the steel. It can also detect presence of any cracks that are within the steel plate or within the steel element you're trying to investigate. We often run this test. This is one of the projects we recently did. It's a metal silo and which was severely corroding. You can see heavy deposits of rust on the steel surface. And this was coated steel. This is not bare steel. This was coated steel. So coatings almost always fail. It's just a matter of when, then if. So it was a coated steel. You have severe deposits of rust. We cleaned the concrete, we cleaned the steel surface using a metal grinder, and then we did the section loss measurements on the silo, and we do this test often. Now, in addition to ultrasonic thickness testing, we have run similar kind of test. One is corrosion potential survey. We have done it on concrete. We can do the exact same thing for waterfront structure or for the structures that are exposed to soil. This is essentially the corrosion potential testing of a steel pile that is encased with concrete and that's exposed to the water. You make a connection to the steel, you use a reference electrode, and you take the measurements. Essentially, the concept is still the same. You make the connection to the steel, you expose the reference electrode to the environment. It can be either water or soil. In case of water, you try to have the reference electrode suspended in water, right, very close to the sheet pile wall or pipe pile, and you take the measurements on the voltmeter. Whereas for the structures exposed to soils, you make a connection to the steel and you place the reference electrode on the soil. You make the soil a little bit moist so that you have some ionic conductivity and you can take the measurements. This is a good example of a corrosion potential survey we recently did on a sheet pile wall. This is a 350 feet long sheet pile wall. We did what we call as a native potential survey. This is when the steel was actively corroding and we measured the potentials at 3 depths. We did one measurement at the mud line, we did one measurement at the water surface, and we did the third measurement midway between the mud line and the water surface. Now, this was without any corrosion mitigation options implemented. Now, when you implement any corrosion mitigation options for, let's say, bulkhead walls or sheet wall walls or combi walls, you tend to install something called as a cathodic protection system or galvanic cathodic protection system. Those are the bulk anodes, like zinc or aluminum bulk anodes welded onto the steel that will protect the steel from corrosion. Once you install cathodic protection system and you take the potential measurements, you see there is a sudden swing in potential. It goes very negative as compared to the native potential shift. The horizontal line you see here is the criteria set by AMP or NACE. That is essentially the minimum potential you require for good cathodic protection or corrosion mitigation. So in this case, all the locations on the sheet pile walls are meeting the NACE criteria and they are being protected against the steel corrosion. So these were all the tests and all the exposure environments. And so in summary, what I'd like to end this presentation with is corrosion is inevitable. Nobody can stop it. We can slow it down or we can delay it. We cannot stop it, essentially. Understanding the health of the structure, understanding what techniques to use. Maybe it can be a conjunction of or combination of on-site testing and lab testing. You can use both at the same time, and you can get a more comprehensive picture of the structure. Also, understanding the exposure environment is critical to designing effective corrosion mitigation solutions for really long service lives. And I think that's about it. I'm at the end of the presentation. I'll be more than happy to answer any questions that the audience might have.
Well, you're not going to be able to answer them all because they came in with a flurry and lots of good ones. And I should just point out that just due to time constraints, Pratik will get a copy of all the questions that have been asked, and he will be able to respond to people individually.
Yes.
Particularly if we don't cover the question in this session here.
Yeah.
I just kind of combined. We had several questions about chloride thresholds, several questions about pH and carbonation. I think I'll just kind of combine them into one general thought you can comment on.
Yeah.
You know, when you have carbonation, you don't always have carbonation alone. You can have carbonation and chloride exposure. Any comments upon the chloride threshold or the corrosivity of the combination?
Yes, that's an excellent point. Chloride-induced corrosion and carbonation-induced corrosion can happen at the same time. ACI document 222 outlines this very well. And typically, when you have an environment where you have chlorides and carbonation happening at the same time, you tend to pick a lot lower chloride thresholds because you have acidified concrete because of carbonation, and then you have chlorides on top of it. So instead of using maybe 350, you might have to use maybe 200 or 250 ppm of chloride as a corrosion initiation threshold. But to answer this question, yes, they work together and they will accelerate the corrosion rates even further than what you would see independently in chloride or carbonation case. Yeah.
Yep, excellent. Several questions on epoxy-coated structure, epoxy-coated reinforcing steel on existing structures.
Yeah.
And how does that affect the selection, or is there creating limitations for some of the test methods when you're dealing with epoxy-coated structures?
Absolutely. Anything that prevents a direct view of the steel would hamper the visibility. So, for instance, we cannot perform corrosion potential surveys on epoxy-coated rebar. Effectively, if we were to do it anyways, you would only be able to tell idea about, or you would be only able to tell or comment on the defects in the epoxy coating that's present on the rebar, but not the entire cell. The bigger issue in performing corrosion potential survey is the electrical continuity. We want the rebar cage to be electrically connected to each other, And if you have epoxy coated rebar, that does not happen. Second is in terms of chloride initiation threshold. Typically, people assume that the chloride initiation threshold is higher for epoxy coated rebar. But then the way I think about it is effectively what happens if the coating is damaged. If the coating is damaged, it's effectively the regular rebar that you're dealing with. So when dealing with epoxy coated rebars, you have a limited set of tests, and you need to uh, view the chloride initiation threshold with a finer microscope and consider all the factors there. You cannot assume a higher threshold or a lower threshold.
Yeah, I've also seen concrete resistivity testing used on those types of structures. It's just an indication of corrosion risk beyond a corrosion potential test.
Right.
We also had a question about, I don't know if you look at the one slide we had the off ramp and you showed the passivity of the repairs, and you had the active corrosion around the repairs, and you mentioned the halo effect. There was a question about mitigation strategies to deal with that risk of corrosion.
Typically, when you perform a concrete patch repair, you're putting a chloride-free concrete right next to chloride-contaminated concrete, and in doing so, you're setting up a concentration cell. You have high amounts of chloride right outside the repair area where you have no chlorides whatsoever in the repair area. So what happens is your anode is now the rebar right outside the repair area, right at the boundary of the repair areas. That's where your new anode is, and that's where the corrosion would happen. Effectively, when you perform the patch repairs, if you don't implement any corrosion mitigation solutions, you are forming another potential area of deterioration right outside the patch repair.
Yeah, excellent. Well, I think that brings us to the time to wrap up our today's webinar. And once again, thank you very much, Pratik. This is the second in a 4-part series on advanced assessment of structures. And you'll see on the screen here, the next session is June 18th, where you have Natalia and Bill Horn presenting, and we'd love for you to come back. They're going to be talking about structural evaluation or assessments of structures after extreme weather events, which I think will be very interesting topic indeed. So if you'd like to register, you see a QR code there on your screen, or you can visit the WeSave Structures website under events. Once again, thank you, Pratik, for the excellent information. If you have further questions, which, as just to point out, there were some questions that we had to come in through the Q&A. Those will be sent to Pratik so that he can follow up on any questions that were not answered during today's presentation. If you also if you want to contact Pratik direct, there you see his contact information on the screen. I'd also just like to point out that if you would like to take this webinar series or other similar presentations to your office, VCS Engineering does offer educational programs, so you can contact VCS Engineering to set up a webinar, seminar, or lunch and learn for your individual group. So that's a wrap for today. Thank you for attending, and let's go save some structures.
Thank you, everyone. Thank you, Chris.
You're welcome.